So today we will try to wrap up the rest of the VCO subject. So mainly we'll quickly finish up this linear time variant analysis, and you'll see there is one part of it which is nonlinear. The part of it which is nonlinear is the phase to sideband conversion. Okay, going from noise to from doing the noise, going from your current noise to your phase of the oscillator is fundamentally linear but time variant. You get folding down of noise. Apart from that, when you go from the phase transfer function to the overall sidebands of the oscillator, there is a fundamental nonlinear behavior there, and that is independent of this of the actual noise behavior, right? So we'll also look at what that is quickly. The second thing we need to do is figure out if you were to design an oscillator, how you would start, what you need to do. Number 3, we need to look at a second set of oscillators, which are the single-ended oscillators. So far we have been looking at differential oscillators. We need to start looking at single-ended oscillators and see how you design them, or rather how they came about, right? And then the basic theory is similar behind all of them. Okay, so let us start off with where we were yesterday. We were looking at the LTV model. The phase of the oscillator was 1 over Q max. We normalized it to this Q max number, which is the maximum charge displacement across the tank. And CIs are the Fourier series coefficients of this impulse sensitivity function. Okay. So C0 by 2 minus infinity to T I of tau d tau. Okay. Plus sigma n equals 1 to infinity Cn integral minus infinity to T I of tau cos n omega naught tau d tau. Okay, this is the expression for the overall phase, and we are going to consider the current, okay, at some harmonic m, which is some Im, capital Im cos m omega naught, and we are going to consider the current at some offset delta omega, because we are interested in the noise at an offset delta omega from your fundamental frequency. Okay, so m omega naught plus delta omega times t, cosine of that. So we are looking at the component at m omega naught plus delta omega, and we said the phase disturbance due to this current noise. Okay, so this is noise current. Okay, we are representing it by this quantity. So the phase disturbance due to this is going to be Im Cm sin delta omega t by, I'll just give you the result. So it ends up being something like this. So Im Cm sin delta omega t by 2 Q max delta omega. So the basic idea is all the other terms will be orthogonal. You will get the term only when n equal to m, and then the n equal to m, when you apply this and simplify the trigonometric expression, you will get the sin delta omega t term. Okay, so even though noise is at m omega naught plus delta omega, it ends up getting folded over to sin delta omega naught plus delta omega. Okay, so that is the important thing to remember. And remember that your VO of t, the output of the oscillator, is some cosine of omega naught t plus phi of t. Okay, this is your phase to voltage conversion, right? Okay, this is your phase to voltage conversion, and remember this is fundamentally nonlinear. Okay, because you have the phase term inside the cosine, and if you really want to find this out, you'll have to, make some approximations, this narrowband, FM approximation, and you'll have to use the Bessel function expressions and so on. But I'll basically give you the final expressions. So if you do this, so VO of t will end up being, let us say, cos omega naught t. So let us say this was a cos omega naught t plus phi of t. You will get a cos omega naught t. This is your fundamental, right? This is your carrier which you are interested in, plus a times, depending on what disturbance you have at a particular frequency, and the amplitude of the disturbance, you can write out the expression. For example, if you had a small a, or rather a Vm, let us say your disturbance could be written as Vm cos omega mt. Okay, you could actually write the expression for these terms, a times Vm times k VCO by 2 omega m into cos of omega naught plus or minus omega m times t. Okay, so in other words, if your phase disturbance was a sinusoid, okay, then what happens is you will get your fundamental carrier plus you will get two things at omega plus omega naught plus or minus omega m. In other words, you will get two sidebands. Okay, in reality you will not only get two sidebands, you will actually get multiple sidebands whose power will keep reducing. Okay, but we will look at only the first set of sidebands. So similarly, the minute you know phi of t, you can actually, using this approximation, you can actually take your noise sideband, stick it inside this and figure out the final expression. So if you had a white noise source, okay, your single sideband noise at delta omega will be 10 log of, let us say the noise was some IN squared by delta f, okay, IN squared by delta f times Tm squared. So remember, so far we have been looking at the absolute noise. You will actually have to, where do I have this expression for, yeah, you see this expression here for VO naught. To get the actual power, noise power, you will have to square this, okay, signal power and noise power. When you stick in this phi nft, the noise phase, okay, so you will get sigma of Tm squared over 4q squared delta omega squared. This is for a white noise source. Okay, so you can see this delta omega squared, 1 over delta omega squared kind of behavior. Okay, and fundamentally you can see that there is noise from many other frequencies, some m times omega naught plus or minus delta omega coming down. What is this guy here? So this is the CMs are the Fourier series coefficients of the impulse sensitivity function. What is sigma of Cm squared? It is the energy of the signal, right? So energy of the signal can also be written as gamma RMS in terms of the RMS of the signal, right? So you can rewrite this in terms of the RMS of the signal, and in fact one expression I quickly gave yesterday also depended on this for the delta omega IS cube. But the basic idea is you can rewrite this in terms of the RMS. So let us quickly do that. Of course, it is actually sigma RMS squared. It's actually 2 sigma RMS squared. So 2 gamma RMS squared. Okay, sigma Cm squared is 2 gamma RMS squared. So the actual expression for this phase noise will end up being 10 log of Im squared by delta f times gamma RMS squared over 2q max squared times delta omega the whole squared. Okay, so obviously what you understand from this is that if you need to reduce your phase noise, fundamentally one of the other things you need to do is reduce gamma RMS squared, right? If you had some impulse sensitivity function, you need to reduce the RMS value of that. You need to reduce the energy, right, in Cm squared. You can also correlate this particular expression to what we derived earlier using the LTI, okay, and see what happens. For example, Q max squared is related to the peak voltage across the capacitor. You can write Q in terms of the capacitance and the voltage, right, and so on, and you can try to figure out, compare this to, in fact, you also know gamma RMS for an LC oscillator. You know that if the oscillator output is cos omega t, the gamma is minus sin omega t, right? The RMS is actually half, so you can RMS squared is half. You can go with this and figure out an expression and compare it to what you had earlier, okay? But the basic idea is, this gives you a certain expression, a nice expression which takes into account folding due to time variance. Now, we quickly looked at flicker noise yesterday, so let's do that also. Okay, so fundamentally the way you adapt this particular model to take into account flicker noise is to write the 1 over f noise, okay, in terms of the broadband thermal noise and the 1 over f noise corner, right, because both are linear. See, one of them, the 1 over f noise is linear, okay, it's 1 over f, it goes, it's not linear, sorry, it's 1 over f. The other broadband noise is flat noise. Between the two regions, you can actually relate the noise terms with through the 1 over f noise corner, okay, and if you were to write the 1 over f noise squared, you can write it as In squared times omega if by delta omega in the 1 over f noise region. Okay, the minute you do this, now you can go back and fit in this guy instead of your In squared by delta f, right, to get your 1 over f cubed region, because you can see you get an extra delta omega here. Okay, and if you actually rewrite this expression for phase noise in the 1 over f cubed region, it's 10 log of Im squared by delta f, okay, over 8q max squared delta omega squared times C naught squared times omega 1 over f by delta omega. Why do we use only C naught here? Because flicker noise is only around DC, right? You cannot have folding of flicker noise down from some other frequency, right? So you have to use only C naught, okay? And that is where you got this term for expression for which we put in last class. C naught is just gamma DC, right? Okay. For example, you can write, we said delta omega 1 over f cubed is omega 1 over f times C naught squared over 4 gamma RMS squared, which is omega 1 over f times gamma DC by gamma RMS squared. Okay, and we said fundamentally the important takeaway from this is that the 1 over f cube noise, the region noise, can be reduced by reducing gamma DC, by making it more symmetric. Okay, so you make your oscillator waveform more symmetric, you make gamma more symmetric, gamma DC reduces, and therefore your omega, the 1 over f cube noise reduces. Understood? Okay. So one last point we have not touched upon, right? We said the oscillator noise has 3 regions. 1 over f cube, where it goes at minus 30 dB per decade, it goes at minus 20 dB per decade, and finally there is a flat noise region. What about the flat noise region? Where do you think that comes from? Because it looks like even if you look at the LTI model, the simplest model, right? You put in broadband thermal noise into the tank shapes it as 1 over f squared. So how do you think you get your flat noise region? What do you think? So as it turns out, you don't get a flat noise region from the oscillator itself. But anytime you want to measure the oscillator, you'll have to put in a buffer. Right? You can't load the oscillator directly. Okay? Similarly, the measurement equipment itself will have a broadband noise floor. Okay? Both of these two things ensure that whenever you measure the oscillator, you will always see a flat noise region. But inherently, the oscillator itself does not have a flat noise region. The farther you go, the tank makes sure that the noise keeps reducing. And that fundamentally we should expect that, right? You don't expect the noise to flatten out. You expect the tank to keep, improving your noise performance. Okay? So, I'll say flat noise region due to noise of buffers and measurement. I'll say measurement noise flow. Okay? Okay, so now we have looked at most things we need to know, actually all things we need to know about the cross-coupled oscillator. Okay? We looked at the different kinds of cross-coupled oscillators. We looked at what the amplitude, output amplitude is. We looked at the LTI phase noise. We looked at the LTV phase noise in some detail. Okay? Now the next question is, I want to design an oscillator. I want to design a VCO. Where would you start? Any ideas? Prathamesh, where would you start? Okay, so let us say, okay, so I'll call this VCO design. So let us say oscillation frequency was some f naught. Okay, so how would you start? Yeah, so you start off with the oscillation frequency. So how would you start? What is the oscillation frequency? 1 over 2 pi root LC, remember that. Okay? Okay, so where would you start? How do you choose L and C? Correct, but that's a fairly wide range, right? You can realize anywhere from 100 picofarad to maybe like 4 or 5 100 picohenry to 4 or 5 nanohenries. So where would you start? I mean, that's a fairly large range. So the amplitude required. Okay. So, okay, very good. So you know that looking at it from a different way. So another suggestion is RP of tank. Okay. Decides the amplitude. So how is it related to the tank? So it is related to the series resistances, the losses in the inductor and the capacitor. So how do you proceed after that? Okay, so you know that. You can get the bias current. No. First I am asking, how do you determine RP? You don't know the value of L, you don't know the value of C. How do you decide RP? Take the Q of the inductor. Okay. No, but you don't know the inductor, so how do you know the Q? That's what I am asking. Okay. So let us look at RP specifically. Okay. So this RP, we know it is due to the losses in the inductor and the capacitor. Okay. However, there is one thing you should keep in mind is that the losses in the inductor are normally much larger than the losses in the capacitor. The capacitive parasitic resistance, okay, are usually much smaller compared to the resistive parasitics of the inductor. Primarily because, you make the inductor with a large, with a wire, you have certain skin effects, right? You have substrate losses due to magnetically coupled losses. So those problems are there in the inductor, apart from the series resistance of the wire itself. However, if you just look at the capacitor, you are looking at the capacitance between certain plates, right? What is that between the plates? It's oxide, right? And of course the oxide will have certain losses, maybe even metal losses. You also have parasitic capacitances which will have losses, but these are usually much smaller compared to the losses in the inductor. So to a first approximation, we will assume that this RP, these losses, come from the inductor alone. Okay. And we will assume that the capacitor is ideal. What do you do next? Okay, you have established this, right? So now, what is the relationship between RP and L? What is the relationship between RP and L? Q into omega naught L. Okay? Omega naught is fixed, right? So it is Q into L. So now what this means is, if you want to approach an ideal LC tank, you need to maximize both the Q and the inductance value, correct? Or rather, you need to maximize the product of the Q and the inductance. Okay. Now, as it turns out, if you take any, a set of inductors, try to design several inductors, the maximum possible Q is not the same for different inductors. However, there will be a certain possible range of values that you can achieve. Okay. And this is, let us say, the typical inductor Q may be, let us say 10 in a particular process. Okay. If you keep changing around the inductance value and, different parameters of the inductor, at a particular frequency, you may be able to get anywhere from maybe 7 to 13, let us say. Okay. It will vary. However, if you look at the product of Q and L, it will be primarily dominated by the value of the inductance L and not by the Q. The Q is varying only by plus or minus 30%. But this is over a change in inductance value of over several octaves. So for example, I may go from L to L by 2 or L to 2L, let us say. I may find only, by changing the parameters of the inductor, there is no restriction on how you lay out the inductor. Remember, what the width of the wire is, right? What the spacing between the wires, how many turns you have. These are all under your control. And therefore, when you change the inductance value over a wide range, the value of the Q you can achieve will only vary by a much smaller amount. So primarily, this is limited by the value of the inductance. So again, to a first order, we will assume that the Q, achievable Q, is constant, and therefore RP is proportional to L. Okay? So is proportional to L. Now, how do you proceed? If you want to, for a given current, you will always have a current consumption barrier, right? I mean, you can assume that, your VCO needs to be designed with a certain maximum current in mind. Okay? Assuming you are going to use all that maximum current, all that current in the VCO, What that means is, to get the maximum amplitude, you need to maximize RP, right? I'll say given IP, right? We need to maximize RP. Why do we need to maximize amplitude? To get minimum noise, right? We know that the phase noise has an expression which has the amplitude of the signal squared in the denominator, right? So you increase the amplitude, your phase noise will drop. Okay, so we need to maximize amplitude. Therefore, given a bias current IT, tail current IT, we need to maximize RP, which means we need to maximize L. Okay. Let us assume that is not fixed. If the outer diameter is fixed, obviously this may be the variation you see in Q may be a lot more. Okay. If the outer diameter is fixed, the variation in Q you may see will still be a lot more. However, the variation in Q times L will still be dominated by L. Okay. So to first order, we will assume this. So we need to maximize the inductance value. Okay. If you maximize the inductance value, what happens to the capacitance? It falls down. Okay. But if the capacitance falls down, what effect do you have on the VCO? The tuning range. Right. So you have to be careful. You may not be able to maximize the inductance value all the time. Okay. There will be a certain trade-off with the tuning range. Okay. So you will have a low tuning range, but let us assume for now that we choose a value of inductance close to the high end, such that we have a moderate tank capacitance value. What ties into this value of C is, if C becomes too small, the parasitic capacitance of the transistors and the inductor will dominate. So you have to be careful about this. Okay. Now, apart from this, we have chosen the inductor value, we have chosen the capacitor value for a given current. What do you do next? Next step is to design the transistors cross-coupled pair. Now, how do you design the cross-coupled pair? You need to design, such that the negative resistance is actually much smaller than the actual losses in the tank. So let us say we choose it to be, for a startup gain of 3, let us say 3 or 4. Okay, let us say the startup gain was 3, so that it will start up very fast, and you're assured that the oscillator will work if you had to tape out this design. What next? GM is fixed. Now, no, IT is already fixed earlier. We are going to use the maximum current possible, right? And based on that, you are going to choose the width such that GM has a certain value. What next? Now you need to ensure tuning range. You have ensured maximum, amplitude for phase noise. You have ensured maximum current consumption possible. Next step is to design for the tuning range. How do you design the tuning range of the oscillator? Well, so far you have probably been using a fixed capacitance in the tank. You need to replace that probably with a varactor. Okay. Okay. You need to replace the capacitance with varactors. But suppose you do this. Okay. Suppose I replace the capacitance with the varactor. The varactor may have a certain Cmax by Cmin. We have discussed this. based on the capacitance tuning curve. Let us say it's some 3 to 1, right? And some parasitic capacitance exists from the transistors. Therefore, I get a certain tuning range. Now, there is a fundamental problem with designing, the full capacitance as a varactor. The reason is, what does a varactor do? A varactor converts some given DC voltage into a capacitance, right? That's what it does. But suppose instead of a DC voltage, I also had a signal alongside. So let us say this was some V bias, this was Vx, this was my varactor. Normally I have been assuming that I am going to give a DC voltage at both these points, right? So it will change the capacitance. Suppose apart from that, on one end I actually have a small signal. What happens? The capacitance will also change at the same rate as this small signal. So what will happen to the frequency of the VCO? The VCO frequency will also get the same signal through a nonlinear process. Again, you have to go back to your narrowband FM approximation, the expression that we looked at before, going from a particular amplitude to phase, right? Going from a particular amplitude or phase to the sideband. In other words, the capacitor, the varactor, actually performs AM to PM conversion. What we are looking at is an AM signal. This is a constant phase with an amplitude. Okay, this gets converted to the phase of the oscillator, and therefore you get sidebands. So you get what is called AM to PM conversion. Okay, and obviously this amplitude varies in a certain manner. The phase and the sidebands of the oscillator will also vary at a certain manner. In other words, if I had any amplitude noise at the output, which I have been ignoring so far, okay, that amplitude noise will get converted to phase noise through this mechanism. Especially since this capacitance is very relatively large, it is a major portion of the total fixed capacitance we have in the VCO. What happens is, the KVCO will be very large. Fundamentally, that's what we are saying. If all the fixed capacitance is just variable capacitance, you have a large KVCO, okay, because the DC tuning voltage is fixed. You can go from 0 to VDD, right? The actual tuning range may be several hundred megahertz. So therefore your KVCO is probably several hundred megahertz per volt, okay, and therefore your AM to PM conversion becomes very significant, because that is related to the KVCO value. You see this here? This AM to PM conversion is related to the KVCO. Okay? So if you have large KVCO, you will get worse phase noise. Okay? How do you handle this? Well, obviously, one of my professors used to say this joke, right? You can call it a joke. This guy goes to the doctor, he says, doctor, it hurts when I do this. Doctor says, don't do it, right? So if you have a large varactor, you have a large KVCO, it causes worse phase noise due to AM to PM conversion. Don't have a large varactor, right? Very simple. But if you don't have a large varactor, you don't get that amount of tuning range. So the way to fix this problem is you take your overall capacitance, you have some varactor capacitance, okay, I'll call the CSW, which is a switched capacitance, okay. In other words, instead of having a continuously tunable, analog tunable capacitance, the analog tunable capacitance needs to be only very small, okay, because why do you need a tunable capacitance in the first place inside the VCO? To embed it inside a PLL, and the DC voltage of the PLL will control the tuning input of the VCO. Why do you need to control the tuning input of the VCO? Because fundamentally the VCO drifts due to voltage and temperature and the frequency changes due to process and so on, right? To tune it to exactly the same frequency, you need a PLL and you need a tunable voltage. However, you can split this into two problems. One is systematic variation due to process. Okay? That can easily be fixed by finding some way to tune the switchable fixed capacitance. What you need to tune with the variable capacitance is only the drift of the VCO frequency due to voltage, temperature and other effects. Right? So the way to really solve this problem, the way people have adopted, is to split this into two independent halves. The first half is the variable capacitance. This is usually a much smaller part. In other words, so let us say KVCO was much smaller value. So even if the supply voltage is 1 volt, you can tune only 30 to 50 megahertz, let us say. This is just a ballpark number. Okay, different people like to use different numbers, but usually this is small. Okay, a few tens of megahertz. This guy, on the other hand, you can have a switched capacitance which goes from maybe very small 0 to a very large capacitance, to the max capacitance. I'll put this in quotes. Okay? The reason is going to become apparent soon. How do you realize the switched capacitance? Yeah, fixed capacitance and a series switch, right? Okay? And now what I do is, I want to tune this capacitance, right? So what I really need is I have a whole bunch of capacitors. Okay? So let us say the minimum capacitance of C0 and so on, maybe some 2 power n C0. I'm going to have a binary weighted capacitor bank. That is easy to control. That is all, right? I'll have a binary weighted capacitor bank with n bits of control. Okay? And now if I turn on the switch, the capacitance exists. If I turn off the switch, there is no capacitance. Right? So I go from 0 to 2 power n plus 1 C0. 2 power n plus 1 minus 1 C0. Okay? However, there is a fundamental problem with these kinds of switched capacitors. The fundamental problem is, let's say I take this capacitor, I would realize the switch using a MOSFET, and this input will be 0 or VDD, right? If it's on, it is VDD, if it's off, it's 0. Unfortunately, I have a whole bunch of parasitic capacitance at this node. Okay? So even though the switch is off, that node, unfortunately, is not completely open. I have a CP, and if this was C0, what is the capacitance when that switch is off? It is CO CP by CO plus CP. Okay? Okay? C max is CO. Right? So the actual C max by C min I get is not infinite. I don't go from 0 to the C max. I have some certain minimum capacitance to C max. As it turns out, there is a trade-off involved here too, because the larger I make my switch, right, the better the series losses, because the switch will have some series resistance, which will lead to series losses in the capacitor bank. And remember, the more number of capacitor banks you turn on, the more number of switches you turn on, more number of capacitors, larger capacitor you want, the series resistance also increases proportionally. and the contribution of the capacitance towards Rp, which we ignored, now becomes a problem. Okay? The reason is this: if I really wanted to reduce completely the dependence of Rp on the capacitance, I would make this switch infinitely large. But the minute I do that, Cp becomes infinitely large also, right? So I can't do that. So there is a trade-off between Q and Cmax by Cmin. Okay? There is a trade-off between Q and the tuning range for your switch capacitor bank. This you cannot fundamentally escape from. Okay? You cannot escape from this. And different people have found out ways to optimize this such that it works. You get the maximum Cmax by Cmin for a given Q. You can look up the literature or look at what other people have done. But there are many ways to implement this. Okay? There are ways to implement this. Since you have a differential oscillator, you can have two single-ended capacitors and switches. You can have a differential switch. Okay? But now you need to bias the center point. Depending on how you bias it, the parasitic capacitance will change. Okay? So when you design your VCO, you can look at all of these things. Okay? All these methods of optimizing the capacitor bank also. Okay? So now what we have said is we need to get a certain phase noise performance by minimizing KVCO, right? That's where we started off. We want to minimize KVCO. We want to get a certain tuning range for that given phase noise. Okay, what next? Are you done now? Sure, you are more or less done now, right? You have designed the transistors, you have designed the LC bank. Okay, what else you need to do? The bias, right? You are more or less done with the VCO core. Now you need to design the bias. What do you do with the bias? Okay, and that's it, right? NMOS or PMOS current source, that's it. Is that all? Unfortunately, it's not that simple. Remember that mixing action which one of you was talking about? As it turns out, that is a very significant, has a very significant effect on the noise of the oscillator. Okay? The reason is, you have 1/f noise and flicker noise. That gets upconverted through the mixing action. Then gets multiplied through the impedance transfer function of the tank. Gives you phase noise. Okay? So actually the bias is also an important part, as you will find out. Okay? In your, when you design this oscillator. How do you design for low noise from the bias? Okay, I have a current source. I want low noise from the current source. How do you do that? Huh? Increase the area. Anything else? What about thermal noise? You're absolutely right. So what you'll find is many of these designs, the bias device will be huge. Okay, sizes you have never seen before. I'll wager that you would never have seen these kinds of sizes before. You will see transistors which are, maybe, well, we'll come to that. But let's see what else is required. Okay, so you need to have very large area. Apart from that, what else? What about thermal noise? Huh? Smaller GM, right? We also know that. Okay, what happens when you try to reduce GM? You take a current source. What happens when you try to reduce GM? How do you reduce GM for a current source? You have to increase the overdrive. The minute you try to start increasing the overdrive, you are reducing the headroom for the the core, VCO core. So you can't do that. So maybe your power supply is, let's say, 1.2 volts. You can have maybe 150-200 millivolts for your transistor, for your current source, and not more than that. How do you achieve all of these together? You need to have, a minimum W over L to achieve, right, a certain VD-SAT for a given current. You need to, minimize GM. You don't increase it beyond that. What else? You need to have huge device sizes for flicker noise. And what you'll find is, you'll find devices of the order of maybe 600, 700, 800 microns width by maybe like 2-3 microns length or 3-4 microns length and so on. Okay, these devices are often huge. Okay. Apart from that, from the mirror device, noise also gets mirrored into the VCO core. People have, normally add a filter in between the mirror device and the main device. Okay, at least you can get rid of the noise from the mirror device. You can't do anything about the current source feeding into the core, but you can do something about the mirror device by adding a filter in between. You can look at all of these things, right? If you look at literature, you'll find all of this. That's it, right? Apart from this, there are certain, the VCO, basic VCO is done. Apart from that, if you really want to design a VCO which has a low sensitivity to supply, you might want to put a, maybe an internal low dropout regulator, right? Something like that. Okay? But yeah, pretty much we are done with these cross-coupled VCOs. Any questions? Yes. Correct. 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 Okay, so what you are saying is what happens when you want to reduce your current consumption. Let us say you want to minimize power consumption. Correct. Why won't you just use the maximum current? That's what I don't understand. That's what we have been assuming. Okay, so let us discuss that. Let us take a particular VCO, okay, and I am going to look at the output amplitude as a function of, let's start off with current, the state current. What will this look like? If you remember, I think the first class on VCOs I asked you to think about this, right? What happens when what happens to the output amplitude when the bias current is changed? What do you think this curve will look like? Okay, very good. So we know from our things that it will be linear. What happens if I keep increasing it? Will it just continue? It will saturate. Why will it saturate? Huh? Which triode region? The triode region. Okay, when does the transistor go into the triode region? Remember that we have said that the transistor primarily goes between on and off. It spends a little time in the triode region, but not a lot, right? Remember, these are cross-coupled transistors. They switch from on to off pretty much, right? So what happens if you keep increasing the current? Yeah, I'm increasing the tail current in the tail current source. That's what I'm doing. Let us look at this first. It directly ties in with what your question. But you're right. I'm trying to see if the other people catch up on this. GM is saturated. Why? Why? I'm increasing current, the GM will only increase. I'm not changing anything else. Okay. Is there any fundamental limit to the output amplitude? Okay. Is there any fundamental limit to the amplitude of the VCO on the lower side? There has to be. It cannot, first of all, it cannot go below ground, right? You have two transistors between the output node and ground. So, of course, it can go up to a certain amount depending on the VDSAT of the current source, plus you will need some headroom for the cross-coupled pair also, right? There is a certain minimum voltage it can go to. On the upper side, is there any voltage is there any limit on the voltage? Supply voltage? Maybe? Yes? Why? Why is there a limit on from the supply voltage? Look at your cross-coupled oscillator. I'm going to look at this oscillator first. Okay. First of all, the output is biased at VDD. Correct? So obviously when the VCO swings, it is going to swing above VDD and below VDD. Right? How much will it swing above VDD? It will swing as much above VDD as it swings above below VDD, right? So as you keep increasing current, the amplitude will keep increasing above VDD also, right? If you neglect, if VDD was much larger than, let us say, the VD sat of these transistors, practically you will get 2 VDD. You can't get more than that, but you can get up to almost close to 2 VDD, right? There is no limit on the upper side actually, because you have an inductor. If you had a resistor or a transistor or something like that, you would have an upper limit. In fact, most of these RF circuits, you will find that if they are inductively loaded, you can actually get much larger swings than you would normally get. And you will see this is all the more important when we come to the next topic, which is power amplifiers, right? But the VCO swings around VDD, okay? It goes up and then comes down. Now, if I keep increasing current, we know that on the lower side there is some limit, okay? So what happens? Start doing this maybe. It will saturate, okay? Now, if I gave you the freedom to choose the IT you want to choose, where would you operate? Where on this curve would you operate? And why? Why? The total voltage? Okay. You are worried that it's going to start clipping here? Okay. Correct. The DC voltage will change. But let us say we don't. Okay. That is if you operate in this region. Correct? Okay. So maybe you don't want to operate that. Okay. Fine. Would you want to operate here or here or here or here or where? Okay, so he's given a particular reason why he doesn't want to operate on the far right side in this region. Where else would you want to operate or not want to operate? Perfect. You want to maximize output amplitude for phase noise. Correct? How do you maximize output amplitude? There is an inherent variable here, RP, which we have not chosen yet. Right? So you can independently choose IT times RP also. Right? So, for any VCO, you want to maximize output amplitude, and as he mentioned, there are certain reasons why you don't want to operate on the far right side. So which is the best region to operate? In this knee region of the curve. Okay? So let us say you increase current till you operate at the maximum possible amplitude of the tank. Or, if I actually look at it in a different way, for a given current, I want to choose my RP such that for the VCO I am in this region. Right? For the VCO, I always want to operate in the knee region. Okay? This curve I have drawn V output amplitude versus IT. For a given IT, I can draw output amplitude versus RP. And I'll have to choose RP such that I am at the knee region of the VCO. Understood? Okay? If you increase further, what happens is this. Okay? Apart from these nonlinear effects where you might get clipping, there will be a certain residual DC voltage across the varactor and so on. Apart from that, what you find is you are increasing the energy. So if you actually move down this curve, you are actually increasing the energy you are putting into the system. However, the signal energy is not increasing. Right? So majority of this will actually end up going into noise. You are increasing the noise. Obviously by increasing IT, you are increasing the noise probably from the current source and the cross-coupled pair. However, you are not getting any signal gains back. So it is a very bad region to operate in. Okay? So for any VCO, the knee region is the best region to operate in.